Hello, everyone, and welcome. Today, we will be studying the chapter on the human eye, exploring a visual guide to biological optics. We will look closely at key components like the cornea, lens, and retina. Let's start by comparing the eye to an instrument you might use every day. Our eyes function very much like a biological camera. In fact, the human eye is a natural optical instrument that uses a complex system of lenses to capture inverted, real images on a light-sensitive screen. Just like a camera lens focuses light, the eye lens does the exact same thing. The aperture of a camera controls light entry, which is perfectly analogous to the function of the eye's pupil. Finally, the camera sensor captures the image, much like the retina does in our eyes. Let's break down this biological camera by looking at its outer structures first. Looking at the front structure of the eye, we have three main parts. First is the cornea, which is the transparent bulge on the front of the eye. Its primary function is to provide the area where most of the light refraction or bending occurs. Next, we have the iris, which is the dark muscular diaphragm. The function of the iris is to control the size of the pupil. The pupil itself is the central opening of the eye, and its function is to regulate exactly how much light enters. Now that we know how light gets in, let's look at what happens inside the eyeball. Moving to the internal structure, we find that the eyeball is roughly spherical and is approximately 2.3 centimeters in diameter. Inside, we have the crystalline lens, which is a convex lens. Its specific function is to provide fine focal adjustments to create an inverted real image. At the back of the eye lies the retina, a delicate membrane containing enormous numbers of light-sensitive cells. With all these physical parts identified, how exactly does light become an image our minds can understand? This brings us to the information pathway, which is a four-step process. Step 1. Light enters the eye and is focused by both the cornea and the lens. Step 2. The retina activates, meaning those light-sensitive cells generate electrical signals upon illumination. Step 3. The optic nerve transmits these signals, allowing them to travel directly to the brain. Finally, Step 4. The brain interprets and processes the signals so that we perceive objects accurately and upright. To keep those images sharp, our eyes have to constantly adjust based on how far away an object is. This incredible adjustment is called the power of accommodation, defined as the ability of the eye lens to adjust its focal length. Here is the mechanism behind it. The lens is made of a soft, jelly-like material. Because of this material, its shape and therefore its focal length is constantly changed by the ciliary muscles pulling or relaxing. Let's look at exactly how those muscles act when we look at objects at different distances. When we are looking far away, our ciliary muscles relax. This causes the lens to become thinner, which in turn increases the focal length. Conversely, when we are looking close up, the muscles contract. This contraction causes the lens to become thicker, thereby decreasing the focal length to keep the image sharp. Even with this remarkable adjustment power, human vision does have a specific range. The normal range of human vision goes from 25 centimeters out to infinity. The closest distance where objects can be seen clearly without strain is 25 centimeters, which is known as our near point or the least distance of distinct vision. On the other end, the farthest point the eye can see clearly is called the far point, which for a normal eye extends to infinity. Unfortunately, as we age, the physical clarity of our lenses can be compromised. One condition that heavily affects vision in old age is a cataract. This condition occurs when the crystalline lens becomes milky and cloudy, which can cause partial or complete vision loss. The modern solution for a cataract is to surgically remove the cloudy lens and replace it entirely with an artificial intraocular lens, which beautifully restores vision. Aside from clouding, sometimes the eye's mechanical ability to bend light just stops working correctly. Sometimes the eye gradually loses its ability to adjust. When this happens, light rays do not focus correctly on the retina, which causes blurriness. In optics, these are known as refractive defects. Let's examine the first and most common refractive defect. This first defect is myopia, commonly known as nearsightedness. The main symptom is that a person can see nearby objects clearly, but distant objects appear blurry. The physics behind this is that the image forms in front of the retina rather than directly on it. Biologically, this is caused by either an excessive curvature of the eye lens or an elongation of the eyeball itself. Fortunately, physics provides a simple optical fix for this issue. To correct myopia, the fix is to use a concave lens of the appropriate power. Here is how it works. The concave lens slightly diverges the incoming light rays before they even enter the eye. This divergence pushes the focal point further back so that it lands exactly on the retina, clearing up the image. Now, let's look at the exact opposite condition. The opposite of myopia is hypermetropia, or farsightedness. The symptom here is that a person can see far away, but nearby objects are blurry, meaning their near point is actually further than 25 centimeters. This is caused by the eyeball being too small or the focal length being too long. The fix requires a convex lens, which pulls the focal point forward so it lands precisely on the retina. There is a third common condition that specifically impacts us as we grow older. This condition is presbyopia, sometimes called old age hypermetropia. Aging causes a weakening of the ciliary muscles and diminishing flexibility of the lens, which causes the near point to recede beyond 25 centimeters. The fix is a convex lens of suitable power. However, for patients suffering from both myopia and hypermetropia simultaneously, the solution is bifocals. Bifocal glasses have an upper part made of a concave lens for distant vision and a lower part made of a convex lens for reading and near vision. To summarize everything we've learned about refractive defects today, let's review this final chart. Here is a quick summary of the defects of vision we just covered. Myopia, or nearsightedness, occurs when the image is located in front of the retina and is corrected with a concave lens. Hypermetropia, or farsightedness, occurs when the image is located behind the retina and is corrected with a convex lens. Finally, presbyopia, or old age hypermetropia, occurs when the image is located behind the retina, making the near point greater than 25 centimeters, and is corrected using a convex lens, or bifocals if combined with myopia. Thank you for studying with me today.